Welcome to our deep dive into making Android BLE work. In this video, we'll explore the intricacies of Bluetooth Low Energy on Android, focusing on reading and writing characteristics and managing notifications. BLE is a powerful technology for connecting devices wirelessly, but it comes with its own set of challenges, especially for developers new to the platform. We'll break down the asynchronous nature of BLE operations, explain why command queues are essential, and guide you through best practices for handling notifications and threading. Whether you're building a simple thermometer app or a complex device manager, understanding these concepts is key. Let's get started by setting the stage for BLE communication on Android. One of the first hurdles developers face with Android BLE is understanding asynchronous operations. When you issue a read or write command, it returns immediately, but the actual data comes back later through a callback. This is a common pattern in network programming, but it can trip up those expecting synchronous behavior. The callback functions such as onCharacteristicRead or onCharacteristicWrite are where you handle the results. This asynchronous nature is not a bug, it's a feature that allows your app to remain responsive while waiting for BLE operations to complete. However, it means you must carefully manage the flow of commands and responses. Crucial limitation in Android BLE is that only one asynchronous operation can be performed at a time. If you try to start another operation before the previous one finishes, it will fail. This is managed internally by a lock variable, often called mDeviceBusy. When an operation starts, the lock is set and it's cleared when the callback is done. Google's documentation doesn't highlight this, but it's vital for developers to understand. Attempting multiple operations simultaneously can lead to errors and unpredictable behavior. Recognizing this limitation is the first step toward writing robust BLE code. Let's look at how the Bluetooth get lock mechanism works in practice. When you call read characteristic, the code checks if the characteristic is valid and if the device is ready. It then synchronizes on the mDeviceBusy lock. If the device is busy, the operation returns false. Otherwise, it sets mDeviceBusy to true and proceeds. After the operation completes, the lock is released in the callback. This ensures that only one operation is active at any given time, preventing race conditions and maintaining data integrity. Understanding this mechanism is essential for managing BLE operations efficiently. Overcome the single operation limitation, serious BLE applications implement a command queue. This queue manages all read and write commands, ensuring they're executed one at a time. Each command is added to the queue, executed, and marked as completed when the result arrives. The next command is then processed. This approach is considered best practice and is used by most BLE libraries. By queuing commands, you can issue them whenever you want and they'll be handled in order, making BLE programming much more manageable and reliable. Implementing a command queue involves creating a queue object and a lock variable to track whether an operation is in progress. When you want to perform a command, you add a runnable to the queue. The runnable contains the actual BLE operation, such as reading a characteristic. If the command is successfully added, you call next command to start processing. This structure ensures that commands are only executed when the device is ready, and errors are logged if invalid operations are attempted. This method also helps with debugging, as you'll see clear log messages for failed operations. Processing commands in the queue, the next command method checks if an operation is already in progress. If not, it retrieves the next runnable from the queue using peek, which allows for retries if needed. The runnable is then executed on a handler thread, ensuring that BLE operations are not performed on the main thread or binder threads. This separation of concerns is crucial for maintaining app responsiveness and avoiding threading issues. By managing the queue and handler properly, you can ensure smooth and reliable BLE communication. After a read operation completes, the result arrives in the onCharacteristicRead callback. Here you check the status and log any errors. If the read is successful, you process the value and then call completed command. This method marks the command as finished, removes it from the queue, and starts the next command. By ensuring that completed command is only called after processing the value, you avoid race conditions and maintain data integrity. This careful management of command completion is key to reliable BLE programming. Sometimes a command may fail and need to be retried. The retry command method checks if the retry limit has been reached. If not, it sets a flag and attempts the command again. If the maximum number of tries is exceeded, the command is removed from the queue and the next command is processed. This approach prevents endless retries and ensures that your application can recover gracefully from errors. Managing retries effectively is important for maintaining a robust BLE connection, especially with unreliable devices. Writing to BLE characteristics is similar to reading, but with additional complexity. You must provide the characteristic, the data to write, and the write type. There are two main write types: write type default, which expects a response, and write type no response, which does not. The default write type is determined by the characteristic's properties, but it may not always be what you want. It's best to explicitly set the write type before writing. This ensures that your operation matches the device's capabilities and avoids unexpected behavior. For writing, check if the characteristic supports the desired write type by inspecting its properties. If the characteristic does not support the write type, log an error and skip the operation. Setting the write type explicitly is crucial, as relying on the default can lead to issues, especially if the characteristic supports multiple write types. By carefully selecting the write type, you ensure compatibility and reliability in your BLE communication. Write data, set the value and write type on the characteristic, then call write characteristic. If the operation fails, log the error and mark the command as completed. Successful, log the action and increment the retry counter. This process ensures that data is written correctly and that errors are handled gracefully. By following this pattern, you can reliably write data to BLE devices and maintain a robust connection. Turning notifications on and off is another key aspect of BLE communication. Notifications allow the device to send data automatically when it changes. To enable notifications on Android, you must call setCharacteristicNotification and write the appropriate value to the Client Characteristic Configuration (CCC) descriptor. The CCC descriptor uses the short UUID 2902. Writing 1 enables notifications, 2 enables indications, and 0 disables them. Understanding this process is essential for receiving timely updates from BLE devices. Notifications and indications are similar but have subtle differences. Notifications do not require confirmation while indications do. From the Android app perspective, both result in receiving a byte array, but indications provide extra reliability by confirming receipt. The stack handles confirmation automatically, so you don't need to worry about it. Choosing between notifications and indications depends on your device and the characteristics properties. Both are useful for receiving updates, but indications are preferred when reliability is critical. On Android, enabling notifications involves several steps. First, check if the characteristic is valid and retrieve the CCC descriptor. Then determine whether to enable notifications or indications based on the characteristic's properties. Set the value to write and enqueue a runnable to perform the operation. The runnable first calls setCharacteristicNotification, then writes to the descriptor. If the operation fails, log the error and complete the command. This structured approach ensures that notifications are set correctly and reliably. After writing to the CCC descriptor, the onDescriptorWrite callback is triggered. Here you check the status and log any errors. If the write was to the CCC descriptor, update the set of notifying characteristics based on the value written. If notifications were enabled, add the characteristic to the set. If disabled, remove it. This allows you to track which characteristics are currently notifying, making it easier to manage and debug your BLE connection. Check if a characteristic is currently notifying. Use the isNotifying method. This method returns true if the characteristic's UUID is in the set of notifying characteristics. By maintaining the set, you can easily determine which characteristics are actively sending notifications. This is especially useful for managing multiple devices and ensuring that you only receive the data you need. Proper tracking of notification state is essential for efficient BLE communication. Android imposes limits on the number of notifications you can enable. As of Android 5, you can turn on up to 15 notifications. Older versions allowed fewer, 7 or even 4. For most devices, 15 is sufficient, but it's good practice to turn notifications off when they're no longer needed. Managing notification limits helps prevent issues and ensures that your app remains responsive and reliable, especially when working with multiple BLE devices. Writing issues can arise when working with BLE, especially with complex devices that stream data at high frequencies. Simple devices like thermometers rarely encounter threading problems. However, complex devices may require multiple commands, authentication, or parameter updates, leading to interleaved reads, writes, and notifications. If notifications arrive faster than your app can process them, you risk losing data. Understanding these threading challenges is crucial for building robust BLE applications. Race conditions occur when multiple threads access the same characteristic object simultaneously. Android reuses Bluetooth GAT characteristic objects, so when a notification arrives, the value is updated in the object. If another thread is processing the same characteristic, the value may be overwritten before processing is complete. This can lead to lost data and unpredictable behavior. Protecting against race conditions is essential for reliable BLE communication. The best way to protect against threading issues is to make copies of the byte arrays as soon as you receive them. In the onCharacteristicChange callback, copy the value before processing. This ensures that your data is thread safe and prevents loss due to overwriting. By always working with copies, you can safely process data on different threads without risking race conditions or data corruption. Android BLE operations are asynchronous and involve multiple threads. Scan results are posted on the main thread, while Bluetooth GAT callback runs on binder threads. To avoid blocking binder threads, process data and issue commands from your own handler thread. Creating a dedicated handler object allows you to manage threading efficiently and keeps your app responsive. Using a handler is a simple and effective way to handle BLE operations safely. In receiving callbacks on binder threads, avoid blocking them with long operations or sleep calls. Blocking binder threads prevents new callbacks from being delivered, leading to missed data and unresponsive apps. Always process data quickly and offload heavy tasks to your handler thread. By keeping binder threads free, you ensure that BLE operations are handled efficiently and without delay. Declare a handler for BLE operations. Use handler BLE handler equals new handler. If you want to run your handler on the main thread, use handler BLE handler equals new handler looper get main looper. This ensures that all BLE commands and data processing are handled on your chosen thread, keeping binder threads free and your app responsive. Proper handler declaration is a foundational step in managing BLE threading. The next command method, execute each runnable on your handler. This ensures that BLE operations are never performed on binder threads, avoiding potential threading issues. By consistently using your handler for command execution, you maintain control over threading and keep your app running smoothly. This practice is recommended for all BLE applications on Android. BLE devices can be categorized as simple or complex. Simple devices like thermometers use standard services and require minimal interaction. Just turn on notifications and read data. Complex devices may use proprietary protocols, require authentication, or involve multiple commands. These devices often present threading challenges due to interleaved operations and high-frequency data streams. Understanding the difference helps you tailor your BLE handling strategy. For simple BLE devices such as health thermometers, the workflow is straightforward. Enable notifications and data starts flowing in automatically. No writes are needed and only occasional reads for features or device information. Threading issues are rare, making these devices easy to integrate. By following standard practices, you can quickly build reliable apps for simple BLE devices. Complex BLE devices require more attention. They may use proprietary protocols, need authentication, or involve multiple commands for user selection, parameter updates, and data retrieval. These operations are often interleaved, increasing the risk of threading issues. High-frequency data streams can overwhelm your app if not managed properly. Implementing command queues, handlers, and thread-safe data handling is essential for integrating complex devices. Devices that stream data at high frequencies, such as 30 Hz, pose unique challenges. Notifications may arrive faster than your app can process them, leading to lost values. Android delivers notifications as soon as they are available and reuses characteristic objects internally. If your processing is slow, new data can overwrite previous values before you finish handling them. Efficient data handling and thread safety are critical in these scenarios. Android's notification delivery mechanism is designed for speed. As soon as a notification is delivered, Android is ready to deliver the next one. If you dispatch handling to another thread, the delivery is considered complete, and new notifications can arrive immediately. This can lead to overwriting if your processing is not fast enough. Understanding this mechanism helps you design apps that handle notifications efficiently. Android reuses Bluetooth GET characteristic objects after service discovery. When a notification arrives, the value is updated in the object. If multiple threads access the same object, race conditions can occur, leading to lost or corrupted data. Always make copies of the data before processing to ensure thread safety and prevent issues caused by object reuse. In the on-characteristic changed callback, copy the byte array immediately. Use system array copy to create a thread-safe copy of the data. This allows you to process the data on any thread without risking overwriting or loss. By consistently copying data, you protect your app from threading issues and ensure reliable BLE communication. After copying the data, post a runnable to your handler for processing. This keeps binder threads free and allows you to handle data on your chosen thread. By using a handler, you can manage BLE operations efficiently and avoid blocking critical threads. This approach is recommended for all BLE applications to maintain responsiveness and reliability. Android BLE is inherently asynchronous, with scanning results posted on the main thread and callbacks running on binder threads. To avoid blocking binder threads, process data quickly and offload heavy tasks to your handler. Never block binder threads with sleep calls or long operations. By following these guidelines, you ensure that BLE operations are handled efficiently and your app remains responsive. Declare a dedicated handler for BLE operations. If you want to run it on the main thread, use handler BLE handler equals new handler looper get main looper. This ensures that all BLE commands and data processing are handled on your chosen thread, keeping binder threads free and your app responsive. Proper handler management is essential for robust BLE applications. Your command queue, execute each runnable on your handler. This ensures that BLE operations are never performed on binder threads, avoiding potential threading issues. By consistently using your handler for command execution, you maintain control over threading and keep your app running smoothly. This practice is recommended for all BLE applications on Android. Let's recap the best practices for Android BLE programming. Always use a command queue to manage operations, set write types explicitly, enable notifications carefully, and handle threading with dedicated handlers. Make copies of data to ensure thread safety and avoid blocking binder threads. By following these guidelines, you can build robust and reliable BLE applications that handle complex devices and high-frequency data streams with ease. If you're looking to get started quickly, consider using a BLE library like BLES for Android. These libraries implement command queues, handle notifications, and manage threading for you, simplifying the development process. By leveraging existing libraries, you can focus on building your app's features rather than managing low-level BLE operations. This is especially useful for beginners and those working with complex devices. Now that you understand reading, writing, and notifications, the next step is bonding. Bonding allows devices to establish a secure connection and exchange encrypted data. In the next article, we'll explore bonding in depth, covering the steps required to implement secure BLE communication on Android. Stay tuned for advanced BLE topics that will take your app to the next level. Summary: making Android BLE work involves understanding asynchronous operations, managing command queues, handling notifications, and addressing threading issues. By following best practices and leveraging libraries, you can build reliable BLE applications for both simple and complex devices. Remember to set write types explicitly, track notification state, and use handlers for threading. With these tools, you're ready to tackle any BLE challenge on Android. BLE is used in a wide range of applications, from health devices to smart home systems. Understanding how to read, write, and manage notifications is essential for integrating BLE into your projects. Whether you're building a fitness tracker, a smart thermostat, or a connected sensor, mastering BLE communication will open up new possibilities for your app. Real-world use cases demonstrate the importance of robust BLE handling. As you develop BLE apps, keep these tips in mind. Always validate characteristics before operations, log errors for debugging, and manage retries carefully. Use command queues to avoid operation conflicts and make data copies for thread safety. By staying organized and following these guidelines, you'll avoid common pitfalls and build apps that users can rely on. Common pitfalls in BLE programming include attempting multiple operations simultaneously, relying on default write types, and neglecting threading issues. Avoid these mistakes by using command queues, setting write types explicitly, and handling data on dedicated threads. By being aware of these pitfalls, you can build more reliable and efficient BLE applications. Debugging BLE apps can be challenging. Use logging to track operations, errors, and retries. Monitor the state of your command queue and notification set. Test with both simple and complex devices to identify threading issues. By employing effective debugging strategies, you can quickly resolve problems and improve your app's reliability. Congratulations on completing this comprehensive guide to Android BLE. You now understand how to read and write characteristics, manage notifications, and handle threading issues. By following best practices and leveraging libraries, you can build robust BLE apps for any device. In the next article, we'll explore bonding and secure communication. Keep experimenting, stay curious, and continue learning to master BLE development on Android.